Nolen is going to talk about reaction-diffusion waves in a random environment.
Thank you. All right. Thank the organizers for the opportunity to be here. I'm very pleased to be here. And I understand I should start by thanking everyone else for being here, because apparently there's a soccer game going on right now. And I should feel flattered that anybody showed up. So I'm going to tell you about reaction-diffusion equation, or reaction-diffusion waves in a random environment. And some of this is the result of collaboration with Lenya Rizhik, Jean-Michel Roch-Joffre, and Antoine Mellet. Here's the equation. It's a scalar equation in just one space dimension. As I'll describe in a few minutes, this last term, f, is a nonlinear function of u. And it's constructed in a random way. It has a statistical structure. I'm going to make assumptions about this construction so that with probability 1, we have classical solutions of the equation. And so for given initial condition, I have an ensemble of solutions going forward in time, solutions to the Cauchy problem. And I'd like to understand the asymptotic behavior of this ensemble in the large time limit. As it turns out, the solutions behave like traveling waves. They develop an interface that moves down the line. That's what this graphic illustrates. I'll explain this in a moment. Okay. So one thing I would like to understand is how the position of the interface behaves in the large time limit. Can we say anything about its statistical behavior, law of large numbers, fluctuations around the mean, large deviations? I'd also like to understand how the profile of the wave itself fluctuates around the mean behavior. Okay? So I'll explain the random setup in a moment. Let me first remind you of some basic properties of this sort of equation when the environment is homogeneous. Okay? And so here's a simple reaction-diffusion equation. And I'll say this is the case with a homogeneous environment, meaning that the nonlinear term doesn't depend upon the spatial variable x. Of course, the behavior of the solution depends a lot on the type of nonlinearity that you choose. I'm going to consider these three cases here: the ignition, bistable, KPP type. In each case, u equals 0 and u equal 1 correspond to equilibrium solutions of the PDE. Okay, you may think of u equals 0 as the unexcited state, u equal 1 as the excited state. Right? So f of 0, f of 1 equals 0. There are three types here, but they really represent two classes of behavior. The first two, the ignition and bistable type nonlinearity, give rise to what in the physics community are called pushed fronts. This has to do with the fact that u equals 0 in both cases is a stable equilibrium. In the bistable case, it's asymptotically stable. This is called the ignition type nonlinearity because f vanishes when u is below this value here, theta. This is sometimes called the ignition temperature. So it models a situation where the reaction doesn't turn on until the temperature rises above this threshold. Bistable, of course, is called bistable because both 0 and 1 are asymptotically stable. You may think of this as the minus the gradient of a two-well potential. I'm assuming that the integral of f is positive so that the well corresponding to u equal 1 is deeper than the well corresponding to u equals 0. Right? So the solutions that arise from this sort of nonlinearity are called push fronts, and that's in contrast to the other case where the sort of solution is called pull fronts. This nonlinearity, this picture represents the KPP nonlinearity. For example, u times 1 minus u. And the main difference is that u equals 0 is no longer stable, it's unstable. And as a result, the behavior of the solution depends a lot on the behavior of the leading edge of the front. There's the region where the solution is very close to 0. Okay? And one can learn a lot about the behavior of the solutions from linearizing the equation around this unstable equilibrium. Okay? So in the other case, the behavior of the front is really determined globally, and linearization doesn't help understand its asymptotic behavior. Okay? All right, so in each of these cases, one can show that if you consider the initial value problem, say with initial data that's compactly supported and sufficiently large over a large enough interval, by sufficiently large I mean it has to be larger than this threshold in these two cases. Okay. So the green blob here represents the initial condition. Under these circumstances, then the solution, as time goes to infinity, will converge locally uniformly to 1, the excited state. Right? So as time increases, the solution develops a plateau where it's very close to 1. Then there's a transition region. And then the solution goes to 0 very rapidly away from this transition region. I'll refer to this transition region as the front or the interface. Right? As time increases, the plateau spreads, the fronts move outward. Okay? And asymptotically, the spreading occurs linearly in time. There are also very special solutions called traveling wave solutions. These are global in time solutions, meaning times positive and times negative. In general, I can't solve the equation backward in time. But these have the property that the solution at time t is just a shift of the solution at time 0. Right? I'll say that these solutions are wave-like. By that I mean as x goes to minus infinity, the solution goes to 1. At plus infinity, it goes to 0. So it connects the two equilibria. And throughout the talk, C tilde will refer to a positive constant. So this is the speed of the wave. Right? These traveling waves are very special because they are attractors. And they govern the large time dynamics of a large class of initial conditions. However, the asymptotic behavior is different for each class of nonlinearities. For the ignition in the bistable case, it's known that the wave speed is unique. The traveling wave profile is unique up to a shift in space. And moreover, the traveling wave is an attractor. Okay? So if I start with initial condition that's wave-like, it's known that as time goes to infinity, the solution to the Cauchy problem. So this is a solution to the Cauchy problem with wave-like initial condition. This is the traveling wave. Solution to the Cauchy problem converges uniformly and exponentially fast to the traveling wave. Okay? This constant tau depends upon the initial condition for u, but it doesn't depend upon time. So there's a one-parameter family of solutions. Okay? So the tau picks out which element of that one-parameter family the solution is converging to. Okay? So it just depends upon the initial condition. In the case of the KPP nonlinearity, the wave speed is not unique. There is a minimal speed, which is positive, and for every constant larger than or equal to this minimal speed, there is a wave with that speed. Okay? If you consider the solution to the initial value problem, then solutions may or may not converge to a traveling wave. It depends sensitively on the behavior of the initial condition that you choose. Okay, so these are basic results for the case of the homogeneous environment. Now let's consider what happens if I add some spatial perturbation. That is, f now depends upon x. And I'm interested not just in localized perturbations, but in global perturbations. So I can't think of solutions as a perturbation of one of these traveling waves. Right? So a simple model which is relevant to some applications is to suppose that f is this product structure, where now f0 is one of the nonlinear functions I've described already, and g is some function of x which satisfies suitable bounds and regularity. Okay? So I'm going to assume that g is positive, bounded away from 0 uniformly, and bounded above. By assuming that it has the same sign, then the nature of the equilibrium points doesn't change. So u equal 1 is always a stable equilibrium. Okay? So for the KPP case, u equals 0 will always be unstable and so forth. Right? Some of the results I described don't require many structural assumptions on the g, but since this is a stochastic PDE conference. I'm going to consider the case where I actually impose a particular statistical structure and then ask how that statistical structure is manifested in the behavior of the solutions. Okay? So I'll consider the case where G is actually a random field that's stationary, ergodic with respect to shifts in X. And if you like, just to fix ideas, think of chopping up the line into intervals and then choosing G to be piecewise constant over those intervals, say taking independent identically distributed values. Okay? So what can go wrong? Well, it turns out that spatial variation in this nonlinear term can have a significant effect on the behavior of the solutions. There may not be a wave speed. One may not have traveling waves in the sense I described. And one may not even have propagation of fronts. For example, in the case of the bistable type nonlinearity, it's known that there can be blocking of fronts. If there's a region where the fluctuations in this nonlinear term are sufficiently large, then there can be a standing wave or a traveling wave with speed 0. And so if you start with initial condition that's behind that region, then as the solution evolves forward, it converges to that standing wave and it does not propagate through that perturbation. Okay? So that's even the case with just localized perturbations. Right? So we'd like to understand what conditions will guarantee propagation of fronts. Is there an attractor, as in the case of the homogeneous environment? What governs the large time behavior of the solutions to the equation? If there is a statistical structure, we'd like to know whether there's an asymptotic speed. And if there is an asymptotic speed, a mean speed, can we describe the fluctuations of the position of the interface or the profile around its mean behavior? Okay. So the answer to these questions depends upon the class of nonlinearity. I'm going to talk first about the first two types that give rise to so-called push fronts. And then later I'll come back and discuss differences that arise in the case of the KPP type, the second class of nonlinearities. Okay? So consider the case where F0 is either bistable or ignition type. So again, U equals 0 is stable, a stable equilibrium. And let's suppose that that last term has the product structure. What this implies is that at each site x, this last term is a function of u, is a graph which fits between the red and the blue curves. Okay? You may think of G as a reaction rate, or in the case of the bistable nonlinearity, as you scale G, that changes the energy barrier for the double well potential that must be overcome for the system to go from the unexcited state to the excited state. Okay. Now, a consequence of the product structure is, of course, that this value theta 0 does not change with x. Okay, so the ignition temperature is the same for all x. However, one can relax this assumption somewhat and consider the case where this value fluctuates with x. For example, there's recent work of Andres Latos. He's extended some of these results to more general types of variations in f. So what does the solution look like? Well, if you were to start with a step function times 0 and plot the solution, you might see something like this. This is the result of a numerical simulation. The black step function is the initial condition of Neumann boundary conditions at both ends. I believe this is for the bistable type nonlinearity. And what you see is the solution plotted at equally spaced points in time. So you see the evolution of the front. The function g was randomly generated. It's piecewise constant. It takes values on each interval which are independent, identically distributed. And so you see that the front propagates forward. Now, I'm going to assume that there is a non-degeneracy condition which guarantees propagation. It's this condition here. Right? So I'm going to assume that at each site the graph of f fits above a this blue curve where the integral of f min here is positive. So this precludes that possibility of blocking, which I described earlier. Okay? So we see that the fronts propagate. We also see that it speeds up, slows down, and as the front moves into regions which are more excitable, where g is larger, or less excitable, where g is smaller, then the solution may develop these local maxima and minima. Okay? If f is periodic with respect to x, then it's been shown that there are pulsed traveling waves. This is like the idea of a traveling wave in the homogeneous environment, except that the profile changes periodically. So within a reference frame, moving at constant speed, the profile undulates periodically. So it repeats itself up to a shift. Okay? So these are called pulsed traveling waves. Of course, if we do not impose a periodic structure on the spatial fluctuations, then the solution will not exhibit this periodic behavior. Nevertheless, you can show that fluctuations do not cause the interface to smear out. Right? The nonlinearity always has a focusing effect. Okay? We can prove that if you take any two level sets of the solution, then those level sets have to stay close. Right? So x plus is a level set corresponding to u equal epsilon. X minus corresponds to 1 minus epsilon. And then there's a universal constant which bounds the distance between these level sets. Okay. We also observe, if you experiment with this code, that there's a kind of loss of memory going on. Okay. Suppose I solve the problem with two different initial conditions. Right. Here, the coefficients, again, are randomly generated, but I use the same realization for both cases. So I take two different initial conditions. On top, it's the one you saw earlier with the step here. I have this wiggly initial condition. I evolve the solution forward in time. Solutions are different. But then I stop the one on top at some time, and then I stop the one on the bottom, not at the same time, but at the time the interfaces reach the same point. And you compare the two, and what you see is that they appear to be indistinguishable. One can explain that through this result here. We can show that there exists what has been called a generalized traveling wave, a transition front that moves to the right. There's also one that moves to the left. And this is a global in time solution to the problem. It exists for positive time and time going to minus infinity. It's unique up to a time shift. It's increasing, so the profile is always moving forward along the line, and it's an attractor. Okay? And that means that if I take any initial condition, which is wave-like, then there's some shift tau. Again, that depends upon the initial condition. It doesn't change in time. And the solution to the Cauchy problem, with that initial condition, converges to this generalized traveling wave exponentially fast. The rate here depends only upon f0 and the bounds on g. It doesn't depend upon the initial condition. Okay? So that
doesn't depend on nonlinearity.
Yeah, it depends upon f0. Yes, f0 is the nonlinearity.
But does it depend on the structure of the nonlinearity?
It depends upon behavior near the equilibrium points.
In the examples, you can say all of them.
So it depends upon the linear behavior near 0 and 1 in that case. Did that answer your question?
So it works in the bistable.
Right. Under this non-degeneracy assumption. Right. So this explains what's going on, because solve the initial value problem, there's this global and time solution, and both of the solutions are converging to that same traveling wave. The shift associated with the convergence is different, so that's why I have to stop them at different times. But if I stop them as they arrive at the same point, I see that the two are the same. Now, it's not necessarily true that there is a wave speed. I can construct initial conditions so that the wave speeds up, slows down, and there is not an asymptotic speed in the usual sense. However, there's still this attracting global and time solution. Okay. This has nothing to do with the random structure. Right? It doesn't use any ergodic theorem. This holds under very few structural assumptions on the G, just the bounds and the regularity to get classical solutions. Okay? Let's suppose that I do have a statistical structure. Suppose I choose G to be a random field, say stationary, ergodic with respect to shifts in X, and so that it has these bounds, regularity with probability 1. Then with probability 1, this result holds. Okay? Then we may ask, well, what can we say about the statistical behavior of this ensemble of waves? Okay. Well, in general, there's not a wave speed, but in this case, fluctuations in the position of the wave average out. We have a law of large numbers for the interface. So let's let x be the interface position. This is the rightmost point where u is equal to 1/2. It doesn't really matter which level set I choose because the interface is stays tight by that bound I showed you earlier. Okay. Then you can show that the quotient x over t converges to a constant, and this constant is independent of the initial condition. Okay. So this is similar to the result in the homogeneous environment, where for the bistable ignition type nonlinearities, you have a unique wave speed. So that's the mean behavior of the interface position. And we can also characterize fluctuations. There's a mixing condition for this to hold. And this is a standard condition that's invoked in proving central limit theorems for sums of random variables. It basically says that the values of G, considered at two different points along the line, are asymptotically independent as you look at points farther and farther apart. Okay? I can show this at the end. But it's a sufficient condition. And if this holds, then you can show that the position minus the asymptotic mean and then normalized by standard square root t scaling converges in distribution to a centered Gaussian. Kappa, in principle, could be 0. One can construct examples where it's non-zero. And in this case, we have a full invariance principle for the renormalized interface process. Okay? So this is a y here. This is a continuous process in t. Okay? For each n, we have a continuous process in t, which is just the interface normalized by the mean and then subtract the mean and normalize it. And you could show that this process converges weakly to a standard Brownian motion. So what this says is that the interface behaves like a Brownian motion with positive drift after suitable renormalization scaling. Okay? And this holds for any solution to the initial value. For the initial value problem with any initial condition, because it holds for the traveling wave, and by the stability of the traveling wave, which I described, it has to hold, therefore holds for any initial condition. Okay? So these traveling waves are constructed as pullback attractors, meaning you start with some initial condition like a step function far back in time, say time minus n, and then you evolve the solution forward in time and consider that family of solutions. Okay? And so in the construction, it's very important to have this interface bound, right? Because this gives you compactness, so that when you take a limit, you obtain something that's non-trivial. So that's essentially how one constructs the traveling waves. Let me say a bit about, let me show this first. So this is an asymptotic result. However, you can observe Gaussian fluctuations on reasonable time scales. So if you do a numerical simulation, we see Gaussian fluctuations. This is a histogram from many realizations, and a quantile plot showing that the distribution of the interface position is very close to Gaussian. I do not have a general bound which says the variance of the interface is always non-zero. In principle, one could construct a medium such that there were negative correlation in the environment, and the variance could be 0. But if the fluctuations are positively correlated, then you can get a lower bound on the variance. Okay? So for example, if G has a structure where these terms GK are independent, identically distributed, then you can show that the variance is bounded below. And as you scale the medium by L here, then the variance can be arbitrarily large, although the speed itself stays bounded. Okay? So this tells us that if I start from an initial condition, take a deterministic initial condition, then as the solutions evolve, this ensemble of solutions evolve, they diffuse. Okay? So it seems that there's no stationary distribution. Right? Actually, there is a kind of stationary distribution if you think about observing the solution at a fixed point in space. So remember the traveling wave property for the homogeneous medium. Was this, okay? The solution, and this says that, so that if I observe the wave as it passes any given point, I'm going to see the same each time I observe it, okay? No matter where I observe it. And this is the generalization of this first line here, is the generalization of the traveling wave property in the homogeneous, in the random environment, okay? So we can normalize the wave so that it's at the origin at time 0. Let me define the hitting time, Tk, is the time at which the interface reaches the point K. So this says that the solution at the time it reaches the point K, in the reference frame centered at K, this ensemble is the same as the ensemble at time 0, centered at 0, up to transformation of the probability space. And pi is measure preserving. Okay? So if I station two observers along the line, and both of them observe the waves as they pass, they will see the same ensemble up to transformation. So in that sense, the profile is statistically invariant with respect to the location where it's observed. Okay? All right, let me explain the basic idea behind this central limit theorem. The main difficulty in deriving this sort of result is that the interface position depends upon the environment in a very nonlinear way through a solution of the PDE. Okay? We don't have a formula for the solution or the interface position. And if I make a mixing assumption about fluctuations in the environment, it's not clear what that implies about mixing in the interface process. Because the problem is diffusive, there's infinite speed of propagation, so the solution and the motion of the interface depends upon the entire environment at all times. Okay? It's useful to look at the hitting time process. Okay? You can show that if you have a central limit theorem for the hitting time process, then you can pull from that a central limit theorem for the interface position, which is essentially the inverse of the hitting time process. So first I can write this. Renormalized hitting time process is the time at which the wave reaches n. This is the mean time. Tau is just the inverse of the wave speed. This is the mean time that it takes to reach the point n, normalized. I can write this as a sum of increments. And because I have this traveling wave, which has the statistical invariance property, these increments are identically distributed. Right? If I think about the time it takes to go from k to k plus 1, that is the same distribution as the time it takes the wave to go from j to j plus 1. Okay? So these are identically distributed. That's good. I have a sum of identically distributed random variables. But they're coupled in a complicated way through a solution of the PDE. Okay? So how do we deal with this coupling? Well, here is where the stability of the wave is useful in analysis. Consider this increment, the time it takes to go from k to k plus 1. What we can show using the stability of the solution to the equation is that the increment depends primarily on the local environment. Okay? If you perturb the coefficients far in the past, okay, let's say L is much less than K. If I perturb the coefficients far in the past, you can show that it does not change much the time it takes the wave to go from K to K plus 1. Similarly, if I perturb the coefficients far in the future, as long as this is far ahead of K, then the time it takes to go from k to k plus 1 is not strongly affected. So what that tells me is that this increment depends primarily, the motion of the wave depends primarily on the local environment. Right? So if I make an assumption about mixing an environment, that means the increments, in terms in the sum, become asymptotically independent if I look at indices far apart. Okay? And so then you can use standard arguments like martingale approximation to get essential limit theorem once you have an estimate on how coupled these random variables are. Okay, so that's for the case of either the bistable or the ignition type nonlinearity. All right, so now consider the KPP type nonlinearity. Again, for the KPP case, u equals 0 is unstable. To fix ideas, let's just set f0 equal to u times 1 minus u. And suppose that that term has a product structure, g times f0. In this case, there may not be global traveling wave solutions, as in the case of the bistable and ignition type nonlinearity. Okay? Even when there are generalized traveling wave solutions, convergence to the traveling wave is not guaranteed. Even when there is convergence to the traveling wave, the convergence is very slow. It's algebraic. Right? So it becomes difficult to use the analysis from the other case to get limit theorems about either the mean behavior or the fluctuations for the interface. However, for the initial value problem in a ergodic random medium, there may be an asymptotic wave speed. Okay? So again, you can show that the interface position divided by t converges to a constant for suitable initial conditions. This is the work of Merck-Frelin and Gertner. As in the case of the homogeneous environment, there's a half line of speeds. There's a minimal speed, c star. And for any speed larger than c star, you can produce waves with that speed. Okay? The speed depends upon the decay rate of the initial condition. Okay? So the solution, the initial condition u is decaying as x goes to infinity. And if you look at the logarithm of u divided by x, if that limit exists, then the solution will have an asymptotic speed, which is determined by this constant u. So this limit uniquely determines the mean behavior of the solution, okay, as time goes to infinity. So we may ask, does the essential limit theorem hold? If this limit exists, does that imply essential limit theorem also holds? The answer is no in general. That is, one can construct initial conditions for which the leading order correction to the mean is larger than square root t. I do not have a sharp characterization at this point of when one starts to see Gaussian behavior and when you see something else, but one can show that for supercritical fronts, that is, for fronts that travel faster than speed c star, one can have essential limit theorem. Okay? That is, for if c is larger than c star, then there's a random function r, such that if the initial condition has this asymptotic behavior, so the logarithm is linear, it's decaying exponentially, and then r behaves like order root t as x goes to infinity, and then there can be a correction which has to be little o of square root x. Then you could show that the solution to the initial value problem satisfies the essential limit theorem. Okay? And again, one can show that the variance is non-zero in many cases, and in this case you have an invariance principle for both the position x and this function r. So this is an interesting difference between the KPP type nonlinearity and the bistable or ignition type nonlinearity, in that in the case of the bistable ignition type nonlinearity, the essential limit theorem is very robust. It doesn't depend upon the particular initial condition. There's some contraction so that perturbations in the tail become are dissipated. In the case of the KPP type nonlinearity, because the zero state is unstable, any perturbations in the tail are amplified, and fluctuations in the tail, or I say tail, I mean the leading edge of the initial condition, are amplified, and they may compete with the fluctuations that enter the solution through the randomness in the medium. Okay? So in general, the central limit theorem may not hold for the KPP case, at least for supercritical fronts. It would be interesting to understand the transition here. Okay, so there are many interesting things to consider. First of all, propagation in multiple dimensions. How can one characterize fluctuations of an interface moving in multiple dimensions in a random environment? The analysis I showed you here relies heavily on the use of a maximum principle. Okay, for systems of equations, propagating pulses, for example, one may not have a maximum principle, so it would be useful to understand how to analyze fluctuations in these systems. Another interesting question is the case of critical KPP fronts. That is, in the case where the speed is equal to c star. Okay? In that case, it's not known what is the nature of the fluctuations. It's conjectured in some of the physics literature that if you look at critical fronts with time and space varying coefficients, that the behavior of the interface will be subdiffusive, and the scaling of the fluctuations would be non-Gaussian after renormalization and scaling. Okay? So it would be interesting to derive that rigorously. And another interesting question is the effect of long-range correlations. Here I've assumed a mixing condition, but it's not clear whether one could get something like fractional Brownian motion limit out of the interface if there were long-range correlations in the environment. Okay. So I'll stop there. Thanks for your attention.
Thank you. Are there any questions or comments?
If the environment were the exponential of a stationary OU process, then the conditions play out. Is it actually?
Right, I'm sending it down from below.
Right. So
Yeah.
is it actually the case that you would not get propagation for that environment?
Probably for the bistable type nonlinearity, that's correct, because with probability 1, you would have some bad region, which would block the front. I don't have a sense for what would happen in the ignition type. So I don't have a result that applies to that case. But yeah, I think for the bistable, you would have blocking.
Thank you very much.